Welcome and thank you for joining us today. Today we will listen to Samuel Gagnon. Thank you so much, Samuel, for presenting your work here. Samuel is going to talk about his research on exploring the interaction between permafrost, ground ice, and soil organic carbon. And I'm going to start with a brief introduction about Samuel, and then we can all listen to his presentation. Samuel is a postdoctoral fellow at Laval University in Quebec City and a former postdoctoral fellow at NSERC PermafrostNet. He is a permafrost geomorphologist whose broad research interests examine the effect of climate change on permafrost stability and the impacts of permafrost thawing and ground ice melting on preglacial landscapes. Samuel received his PhD from Laval University in 2020 under the supervision of Dr. Michel Allard, and his thesis investigated the impact of climate warming on the morphology and activity of ice wedges in the Narsjuk River Valley, Nunavik, and using an integrated approach, including modeling, remote sensing, laboratory analysis, centered around fieldwork. He then went on to obtain a specialization in cryostratigraphy by doing a postdoctoral fellowship with Dr. Daniel Fortier at the University of Montreal. He investigated the long-term stabilization process of Thermo-erosion gullies on Violet Island and the performance of geotechnical methods to mitigate permafrost warming on a road embankment near Beaver Creek, Yukon. For his current position at Laval University, Samuel is pursuing an additional specialization, looking at the role of ground ice in the development and stabilization process of thermokarst lakes and drain basins in Old Crow Flats, Yukon. Thank you again, Samuel, for presenting your work here. It is much appreciated. And yeah, you can start. The floor is yours.
Thank you so much, Zaki, for this very nice introduction. Thank you for everyone who's attending today. It's very nice to have all these people participating. I'm very happy to have this opportunity to discuss my research and hopefully just spark some conversation about some subjects. I'm going to do an overview of a lot of my research and the links I've seen from them. A lot of it has been about carbon and ground ice. So currently a postdoc at Laval University, and before that I was University of Montreal, as Zaki mentioned. And in between the two, I did a 1-month postdoc with PermafrostNet. But before that, I had been involved with PermafrostNet for about a year and a half. So that's why I've been I was invited today to present, and also I'm involved with the network. I've been involved for a couple of years now. So as I mentioned, I'm going to be talking today about two main themes that have been driving most of my work so far. So in the past few years with my postdoc, I've been more focusing on the ground ice, but I've seen a strong link between the carbon and ground ice, and I wanted to explore that a little bit today in my presentation using the research I've been doing over the past 10 years or so. So I'm going to go fast over this introduction because I'm sure all of you are well aware about the carbon in the Arctic. So permafrost is one of the largest organic carbon reservoirs in the world. And this carbon has been for thousands of years locked away in frozen ground and not actively participating with the global carbon cycle. And the big question that has been driving a lot of research over the past 10, 15 years is what happens to this carbon when it is freed and the active layer becomes deeper with climate warming and permafrost warming and the active layer deepening. And the idea is that with permafrost thaw, new carbon that was not previously available for decomposition will become available and will be emitted into the atmosphere in the form of methane or CO2, thus adding new carbon to the atmosphere and causing more warming. And warmer climate causes the active layer to become deeper, and thus we have newer carbon that was previously locked away and not contributing to the carbon cycle becoming available, and so on. We have a positive feedback on the global climate. And this, so the study of carbon and the fate of carbon in permafrost with climate warming is really an entire subfield of permafrost research that is dedicated to questions pertaining to carbon in permafrost. And I find there are two main questions driving a lot of the work in this subfield. And the first big question I want to explore this afternoon, is how much carbon is there in the ground? And this might sound like a simple question, but it's a challenging question. It's a big question because all of the models and predictions about future emissions at the regional and circumpolar scales rely on those large-scale estimates. And at the moment, our best guesses are from being perfect. And so why is it so difficult to have good soil carbon estimates? And there are two main problems with carbon estimates. First, there are large gaps in the spatial coverage of the samples. We only have a very small number of data points for such a vast region. And those data points are mostly clustered together, which is not very good for spatial viability. And the second problem is that large mapping polygons are usually used to upscale carbon contents from sparse measurements, which causes large uncertainties and creates maps that are only suitable for large-scale analyses. And I think we've all been at some point guilty of this. We use those big maps that are made for at the circumpolar scale for our regional or even local analyses. Well, in fact, they are not suitable and they were not made for this purpose. It's also very common to use land cover maps for the upscaling process, and those maps are often not appropriate. They have little connection with the soil organic layers and the carbon content, so they're not suitable for the upscaling process. So there are two main solutions I see that we can use to improve our estimates. We could increase the number of samples of data points, but that would be very costly to do it evenly across the Arctic. And there are important logistical constraints due to the remoteness of many areas of the Arctic, as you all know. So the other thing we can do is improve our ability to upscale field measurements. And that's the approach that we chose for this study. And to do so, we use geomorphological features because there is a strong connection between landscape features and soil connection. And we could also add to this to ground ice, which we will come back later in the presentation. So for this project, we mapped the geomorphological landforms with the help of geomorphological and the geological history of the valley to produce a fine-scale geomorphological feature map with surface deposits that we use to upscale carbon content measurements from samples we had collected in the field. So mostly it was image analysis and validation with field samples and surveys. And the results have shown that the geological and geomorphological history of a given area should always be the first tool used when investigating soil carbon content, because the heritage from past climate variations is very helpful to explain the origin and the formation of features observed in the landscape, and therefore very helpful for interpretation of those landforms and also for the soil composition. We also found that mapping landforms is very interesting because of the strong connection between landforms, soil types, and carbon content. So by understanding the landforms, we can more easily predict the sediments we'll have, the context in which they were deposited, and therefore the carbon content we're likely to find in some areas. And even though soil sampling and field work will always be necessary, mapping geomorphological features and understanding the impact of the geological history on the landscape can considerably improve estimates by using means widely available and at limited costs. So means to improve soil carbon content estimates exist, and it's an ongoing process. We're always trying to improve the way we're producing maps at large scale and in smaller scale, so for the work we're doing. Even if they're still largely imperfect, it's still an ongoing process. But now the question is, what happens to this carbon once permafrost starts thawing, which is our second big question about carbon. What are the gases emitted from permafrost and how much of it is emitted into the atmosphere? And this is very important because this directly affects the carbon cycle and the climate warming and the global climate. And to answer this question, I had a project where we measured and estimated carbon emissions from permafrost. But again, measuring greenhouse gases is not that simple. We can use indirect methods such as eddy covariance towers or modeling. But the big problem with that is that there can be a lot of uncertainties with those methods, and it can also be very costly to deploy more than one tower, for example, or multiple instruments. Or we can also use direct methods, such as closed chambers, which you can see here, which are very simple to use. They basically are closed boxes that we put on the ground, and we measure the increase in gas concentration over time, thus calculating fluxes. However, the big problem with closed chambers is that they demand multiple measurements every day, and we have to be physically there to make the measurements. So it's both time-consuming and labor-intensive. Some automated systems exist, like we have here a LICOR system with chambers that can be connected together to a same power unit, but they can be sometimes prohibitively expensive, especially if we want to have multiple chambers in multiple locations. So it can be a substantial cost to have them, especially with the power constraints in the Arctic. So in response to those problems, I decided to build for this project a low-cost automated system using cheap greenhouse gas sensors and components, and also use open source electronics to measure emissions from the tundra. So the goal of this project was to produce a system that could be used and easily replicated by other researchers, and thus increase the number of measurements we have from field experiments. So this research was carried out in near Salouet in a polygonal peatland, as you can see here. So in northern Quebec, all the way up here. So I made measurements in different environments. We, of course, had natural conditions to measure I have a baseline of the CO2 emissions from the ground. We had a chamber installed in an open top chamber, which is this small little greenhouse with the top open. And this open top chamber can simulate the climate warming we expect to have in about 50 years of about 2 to 3 degrees, because we wanted to see the impact of warming on the greenhouse emissions. We also had greenhouse gas emissions. We also had a chamber in the trough between two polygons to see the impact of water saturation, because the water table was often above the ground or near the surface in that location. And we finally had a chamber in an area with no vegetation at the surface, because we wanted to measure only the part of the gases emitted from the ground and not from vegetation respiration. And of course, since we had a new instrumentation, we wanted to have reference measurements. So we use this reference system here with an infrared gas analyzer and a potable chamber, so we could compare the two systems together and see if we're performing well. And despite having some trouble in the field with the system, the results were really, really good. Almost no difference between the commercial system and our system. So we're very happy about that. And on top of that, our system was way cheaper. So for the same price as this one chamber with the analyzer here, we had the 4 chambers that were working at the same time. So it was a success in that regard. But looking at the variations in ecosystem respiration, so the CO2 emitted in the dark chambers, and the environmental variables, with no surprise, we concluded that temperature was the main driver of ecosystem respiration, both at the diurnal and seasonal scales. But what was really interesting in that study is that from our measurements, we noted that most of the respiration occurred in the top 10 centimeters of the ground. So even with the progression of the active layer during the summer, deeper and deeper, and we can imagine with climate warming in the future, this did not necessarily lead to that much more carbon emissions, because most of the respiration was done at the surface. We also noted that the water table depth also played a significant role in this at the seasonal scale. So when we had a high water table that is very near the surface, or even at the surface or above it, this significantly reduced or even stopped respiration altogether, while a deeper water table led to favorable conditions for more emissions. And up to a certain point, because as I mentioned, past a certain point, most of the respiration was done at the surface anyway, so didn't change that much. So this means that even if the active layer deepens and there is more carbon available for decomposition, this carbon will not necessarily lead to that much more emissions if the water table remains high, which is very common in the Arctic because of the limited water infiltration, since permafrost is kind of an impermeable layer limiting water infiltration downward. So more and more, we understand that greenhouse gas emissions from permafrost thaw over the next decades will be much more gradual than we initially anticipated about 15 years ago, 20 years ago, when the idea of a carbon bomb would highly contribute to a positive feedback on the global climate and warming was much more of the trend back then. As I mentioned, local conditions can significantly reduce microbial activity, such as the high water table, is far from having similar conditions to the top in the active layer carbon. So we have different temperature, aeration, water content that can all affect the rates of decomposition and microbial activity. Plants may also play an important role. I didn't talk about it and I didn't really study it, so I just want to mention it here because with the greening and shrubification of the Arctic, depending on the area, it's possible that the carbon that is released may be offset by the carbon sequestered by the plants, whether it is in bigger ligneous plants like shrubs or the accumulation of peat on other wetter areas. So as I said, we understand that carbon released through the deepening of the active layer will likely not be a major source of carbon emissions into the atmosphere with the net balance. However, as you all know, warming of permafrost does not only lead to a deepening of the active layer, and a lot of focus in the past few years has been shifting towards the rapid release of deep organic carbon through thermokarst, so mass movement caused by the melting of ground ice in ice-rich areas. In which case, carbon that was deep in permafrost is now rapidly exposed at the surface, and then this carbon can be decomposed much more rapidly than it would normally because we have better conditions facilitating the decomposition. In addition, we can have also release of carbon into water, so streams or some seas, whatever, on coast. And then other processes can lead to faster carbon emissions that would normally in permafrost thawing. So if we think about thermokarst and how it works, it is essential to have a good characterization of ground ice because ground ice is at the center of thermokarst processes. Therefore, if we are to better understand and characterize permafrost carbon release, we also need to characterize ground ice. Ground ice is found pretty much everywhere we have permafrost and will vary in proportions depending on the type of soil. But what's really interesting about ground ice is that it can increase both permafrost vulnerability and resilience. So on the one hand, ground ice melting can cause subsidence and water ponding or expose deeper layers by landslides or thermo-erosion, resulting in a positive feedback or multiple feedbacks on permafrost degradation. So more and more degradation because we have more ice exposed, more melting, etc. But on the other hand, this ice requires large amounts of thermal energy to melt due to its large latent heat of melting and can therefore reduce the progression of the active layer and thus increase permafrost resilience to climate warming and extreme weather events such as very warm summers or heavy precipitations. Therefore, understanding how ground ice affects permafrost stability and thus how much ice there is in the ground is very important. Whether it is to understand where or how we build infrastructure so that it doesn't collapse over time, or just to understand what will be the implications of climate warming in periglacial landscapes and the global climate. But again, characterizing ground ice is very difficult because there's no direct method to measure it without digging or coring. And the challenges, as you can see there, are pretty much the same as for carbon content. I basically use the same one. So large gaps and data points clustered together, large mapping polygons to upscale a few data points we have. And on top of that, we also have the quality of the data available and how we describe the ice can also cause problems. For instance, many older reports were reporting the ice content based on visual inspection of the cores, which is highly unreliable. We also have, the way we express ice, is it excess ice or total ice content, which makes a big difference in what we're going to observe in the landscape. Because if we talk about total ice content, it doesn't exactly tell us much about the subsidence potential. So all of this requires a common language. So more and more we see that we need to have a common set of standards if we are to do large-scale measurements. And this is in part what I was tasked to do when I joined PermafrostNet as a postdoc in Theme 1. So just quickly, just have a small parenthesis on PermafrostNet Theme 1. So the objective of the theme is to improve the understanding of ground ice loss and its consequences through characterization of permafrost in Canada, so that the prediction can represent processes during thaw and have relevant subsurface input such as ground ice content. So in large part, this involved the characterization of ground ice and developing infrastructure to share and use this data. And I don't want to spend too much time on this because Nick Brown, a data specialist with PermafrostNet, did a fantastic talk about permafrost data and the development of standards and database structure, which I invite you to check on the PermafrostNet YouTube channel. Data handbook that you could have access really available online. It's very useful for, yes, sharing your data and making it easy for publication and open access, but also just to organize your data in general for future use, I strongly suggest you have a look at this handbook. But a big part of my efforts while I was a postdoc with PermafrostNet was the publication of existing data. And so if we go back to our possible solution to improve our ground ice estimates, or it was carbon initially, one of the solutions was to increase the number of data points. But for theme 1, rather than relying solely on new data, which takes time and money and efforts and resources to go in the field and bring back and analyze and then finally publish, we focused our efforts on finding and publishing existing data, but that was either unusable or not easily accessible. Because while in the carbon community, they have been relatively good at centralizing their data together for sharing and creating a unified database, it's not really the case for ground ice, at least not in Canada. So for us, we focus on existing data in Canada from older reports that were never digitized or not, as I said, easily usable. And we inputted them in a standardized way in the PermafrostNet database structure, Pingo, which we can see here, and you have access. If you type on Google PermafrostNet ERDAP, you'll have access to all of the data we inputted and much more that's available online, so that the data is easily accessible and is also interoperable on different systems. And since this was a monumental task for the entire Canada, we decided to focus our efforts on areas with not much data available to really increase the number of data points in areas with large spatial gaps. And in this case, we decided to focus on the polar desert in Canada. So with the collaboration of the HQPs in Theme 1, we were able to retranscribe borehole data from 2 reports and produce metadata for a total of 253 boreholes, which is invaluable information for permafrost conditions in the polar deserts. And this is, as I said, this is now readily available for any researcher through the Pingo database here. So we saw that ground ice characterization, as for carbon, is a big challenge. But once we have the information, what can we do with it? How can it be useful? And the answer to this is pretty much infinite. All of your research probably touching to ground ice, either directly or indirectly. But I want to insert this today with 2 applications I've been using in my research in the past. So the first thing I want to talk about is using ground ice as a record of the past and as an indicator of current climatic conditions. Because ground ice is largely affected by the climatic conditions at the time of formation, so the ice can give us clues about the conditions when it formed. And to illustrate this, I'm going to use ice wedges. So ice wedges, you probably have all heard of it, so I'm going to go rather quickly on this, but ice wedges are one of the most widespread form of ground ice in the Arctic. They form during cold winter when it's very cold temperatures and the soil contracts and cracks. And then we have water infiltrating the cracks, forming an ice vein in permafrost. And then if we have the same process repeating itself over years, decades, centuries, we have the accumulation of ice veins until we have an ice wedge in the landscape. And it will form polygonal tundra. So that's the physical manifestation of those ice wedges in the landscapes. But ice wedges are particularly interesting because they are very good climate change indicators. So during colder periods, they are active and they are growing, accumulating ice, while during warmer periods, they become inactive, dormant, or even in degradation if we have permafrost that is warming quite a bit and a deepening of the active layer. In Nunavik, where I did my research on this, during the first half of the 20th century, ice wedges were generally dormant. Well, starting in 1946, because of a cold spell, they were reactivated and formed upgrowth forms, which you can see here, which are new stages on top of the ice wedges indicating rejuvenation, new growth. And this was reported by Jennifer Casper and Michel Allard in the early 1990s. But so here you see the cooling trend. So in Nunavik from 1946 approximately to about 1992. And they did their work in the early 1990s. But in 1992, the cooling ended. So the main goal of this project was to determine the impact of climate warming and its severity on permafrost by investigating the state of the ice wedges. And what was particularly interesting with this project is that we had the unique opportunity to revisit a study site that was studied 25 years ago, before the beginning of climate warming, and make direct comparisons of the impact of climate change on the landscape. So looking at changes in ice wedges, but also the effects on vegetation, surface hydrology, and landforms. The project was carried out in the Nasayurak River Valley in Nunavik, where we revisited 16 subsites that were studied in the early 1990s. The valley is composed of multiple fluvial terraces of various levels and ages on both sides of the valley. And because of this, the terraces also have different soil compositions. In general, we saw that the older terraces had a thicker organic layer, more time for accumulation, while younger ones had a thinner organic layer or just no cover at all when they were of lower level. And this greatly affected the age, the activity, and the state of the ice wedges. So we observed that the active layer, when we went in 2017, 2018, the active layer was 1.2 to 3.4 times deeper than what it was in the early 1990s. And this caused a widespread degradation of the ice wedges in the valley, particularly around 2010, when it was the warmest year on record in the area. And that's when the deepest active layer was recorded. In fact, we found that while 94% of the ice wedges in 1991 had upgrowth forms, which were reported by Jennifer Casper and Michel Allard, when we went back, only 13% of the 55 ice wedges that we unearthed still had upgrowth forms in 2017. In addition, the deepening of the active layer did not only cause the degradation of the upgrowth forms, but also caused the main body of the ice wedges to become deeper than what they were in the early 1990s. So this indicates that not only the upgrowth forms have melted, but also that the active layer reached depths leading to an unprecedented degradation of the ice wedges. Hence the interest in looking at this type of ground ice for the how the active layer evolved with this very rapid and significant warming over the past 20-30 years. And this degradation can substantially affect the landscape by causing ground subsidence and gulling. So you see here, if we have a sufficiently big ice wedge that keeps melting, we can have a large cavity forming until the top collapses. And then this section can channel water and then eventually form a gully, which can grow in size, continue eroding. So positive feedbacks, eventually leading to a thermal erosion valley. So it can completely change the local hydrological connectivity and on top of that, the geomorphology of the area. Which brings us to the second reason I've been studying ground ice, which is understanding the impacts of ground ice melting on permafrost. Because the main physical manifestation of permafrost thawing is ground subsidence, which requires excess ground ice to occur. And the first example I have to illustrate this is the Thermo-erosion gully, as I was just talking about in Salouet. So Thermo-erosion gullies formed by the combined thermal and mechanical action of moving water and are very common in polygonal networks due to the interconnected troughs that can channel runoff water. And the thing is that ice wedges can melt very rapidly. So Thermo-erosion gullies can form very fast. Within a single thawing season, we can have melting of the ice wedges and then collapse of the ground, thus channeling even more water and thus creating a positive feedback on the landscape. The formation of the gullies can significantly affect permafrost environments by changing landscape morphology, and then which causes a change in vegetation. For example, we can have drying of vegetation because we have more drainage, which creates a shift in vegetation. And of course, changing hydrology. We have now a channel bringing all the water together rather than having more dispersed in the landscape. And for this project, we were looking into the effects of the long-term stabilization of gullies on permafrost stability, its ground ice content, and landscape evolution. And to do this, we compared two gullies together. One that recently formed in 1999 within a single thawing season, was very active for the 10 years after. Then the activity slowed down, but it's still active today. And another one here, as you can see, no sign of erosion for this one. It's been stable for decades, if not over a century. So no sign of degradation for that one. And the gullies were were located on Bylot Island in the high Arctic in Canada, specifically in the Cyr Lake National Park. And our goal was not to investigate the processes of gully formation and stabilization, because those have already been well documented and are pretty much well described, but rather to look at the long-term effects of ground ice melting and the associated permafrost thawing on permafrost stability and its resilience to future disturbances. What is this? In other words, what is the state of permafrost after long-term stabilization of a big disturbance? In this case, we chose a thermo-erosion gully. And we found that the gullies had a profound impact on the landscape, with no surprise. But despite that, permafrost is able to recover to conditions similar to those predating the disturbance and thus shows resilience. So if we look here, I'm at this conceptual diagram of the degradation and stabilization of a gully. So we have our initial undegraded polygonal network. We have a big disturbance leading to ground collapse, formation of a gully. And stages 1 and 2 show the degradation stages of the gully, and we can have over time stabilization. This stabilization can be go back to degradation, to initial degradation, and go back and forth for many years, even decades, until we have a final stabilization where we have a vegetation cover that is sufficient to really stabilizes the slopes. The slopes have a lower angle, so they're not as unstable. And eventually we have our new state of permafrost. So in this new state, we have a near permanent scar in the landscape. We have the gully that is stabilized, changing the snow accumulation patterns, the hydrological connectivity. But looking at the permafrost state, so its thermal state and the ground ice content, we noted that the ground ice content and the thermal state with the deepening of the active layer that is similar to what it was before. So both were very, very close to what they were before degradation. So we compared it with a undegraded site and noted that permafrost was resilient enough to go back to what it was before the disturbance. And having all of this ice that reaggraded with permafrost recuperating means that this ice can resist to other future disturbances and thus increases permafrost resilience to other disturbances. Another example I have also from Bylot Island is an active layer detachment slide. So the slide here occurred in 2019 following a particularly wet summer when multiple slides were observed in the valley of the national park. They were really I think there were over a dozen of slides all over the valley that formed due to the very, very high precipitations early in the summer. So in this case, the top layer, the active layer, was saturated with water and started sliding on this ice-rich permafrost. And then after the formation of the slide, there were other geomorphological disturbances occurring in the newly formed depression. So we had channeling of the water, and then because of that, we had also thermal erosion forming and thus continuing the degradation on those slides. And usually, active layer detachment slides form during warmer than usual summers when we have a depth of thaw, so a deeper active layer that is greater than normal, and thus it leads to a failure on the slopes and then slides on the ice-rich permafrost. But in this case, heavy rainfalls were really the main factor leading to the detachment failure. And since climate predictions for the Arctic point to a shift in precipitations towards more rain by the end of the century, this could mean that we're going to see more and more slides in the next decades. And well, this is not really surprising, but our question was, and is, we're still investigating this, will the high Arctic experience more detachment failures than at lower latitudes for a similar increase in rainfall? Because in the higher in the Arctic, we have lower temperatures. So in general, we have a relatively thin active layer. And because of this, we have a transition layer that is closer to the surface. The transition zone or transition layer is a layer at the interface between permafrost and the active layer that is very ice-rich, richer than the rest of permafrost usually because of variations of the active layer depths at the scale of decades to centuries that contribute to enrich the zone. And since this layer is closer to the surface than at lower latitudes, it is also more vulnerable to extreme events if we have very, very heavy rains or very, very warm summers, leading to a permafrost thaw that is out of the ordinary and therefore more vulnerable to disturbances. So understanding the ground ice content and its vulnerability to extreme events is very important in order to predict changes in Arctic landscapes. So far, we have seen how carbon and ground ice relate to one another in terms of determining how much there is in the ground and what their impacts on other environments. But now I would like to finish by briefly discussing how they interact with one another. Because as I mentioned earlier when discussing carbon, rapid exposure of deep organic carbon can lead to substantial carbon release. And melting of ground ice, thermokarst, is at the center of rapid permafrost disturbances. And the example I have comes from my current postdoc, for which I've been working in Oak Grove Flats in Yukon, northern Yukon. So Oak Grove Flats was not glaciated, just to give you a little bit of context, not glaciated during the last glaciation. And because of the configuration of the ice sheets, a proglacial lake formed where we currently have the flats. So you see here, this was all Old Crow Lake, a proglacial lake. And because of this, the flats are characterized by fine-grained lacustrine deposits, so silt and clay, that are very, very ice-rich. And on top of that, there are also well-developed ice-wedge networks with very big ice wedges. So the flats are very ice-rich, and because of that, they are also quite dynamic due to the thermokarst processes. So we have thermokarst lakes forming with the ground subsidence, water accumulation, but then those lakes can eventually drain, usually associated with very heavy precipitations during summer. So the water level goes higher than the lake limit, overflows, and this overflow creates a channel that will create thermal erosion. And as we have more and more thermal erosion going into permafrost, melting the ice as well, we lower and lower the level of the lake until it partially or completely drains. So it's very common for this type of environment. We have multiple generations of thermokarst lakes, drain basins overlapping one another because they form, they drain, they form, they drain, etc. in the environment. Here, I just put some pictures of show you, since it's a very ice-rich environment, some pictures of this. So we have first on the left, a cross-section of an ice wedge exposed on an eroding shore of a large thermokarst lake. So once exposed, the ice melts much more rapidly, which can lead to a positive feedback on permafrost degradation because we have more ground collapse and then more ice can melt, etc. And then on the right, we have a permafrost core, a very ice-rich permafrost core along with its CT scan. So the CT scan is a medical scan we use for seeing the difference between the sediments and the ice. So the ice is in the darker gray, while the sediments that are denser are in lighter color. You can see most of the core is ice, and therefore, if we have warming and melting of this ice, it can lead to substantial thaw subsidence and cause substantial change in the landscape. So to talk about ground ice and carbon, I wanted to talk about this example where we have an eroding shore here along a larger lake, a large thermokarst lake. So on this side of the lake, we have dominant winds forming larger waves that come in crashing onto the bank and contribute to shore erosion. But because we have such high amounts of ground ice, the erosion is much faster due to the thermal erosion. So we have the water bringing heat, and then we have exposition to atmospheric conditions. So air and also rain can fall and contribute to add heat as well. So exacerbating the degradation. So as I mentioned earlier at the beginning of the presentation, the deepening of the active layer can somewhat contribute to more carbon decomposition, but the largest sources of carbon may actually be the process that lead to rapid carbon release at the surface. So here when the ground collapses on the eroding shore, large chunks of peat can fall in the water, and then we have deeper carbon exposed as well. It can also be eroded and fall in the water. And rather than being slowly decomposed as a big chunk, it can fall in the water and kind of be churned by the wave action into smaller pieces. And this can be more easily decomposed, and thus the carbon can be released more easily. So for this project, we plan on investigating the effects of waves on the decomposability by doing incubations of chunks of ground and peat taken at different places on the shore at different heights. So, an intact chunk of peat versus one that's been turned and broken down by the wave action. And our hypothesis is that the churning by the waves could increase carbon emissions and carbon release into the water as well. But the thing here I want to highlight is that ground ice is largely responsible for increasing the amount of carbon available for decomposition, and also by accelerating this decomposition by exposing the carbon to conditions that are much more favorable for its decomposition compared to death especially when we have an exposed cliff caused by ice melting, and then we have material falling off. Then we have deeper carbon that would not be normally exposed or not exposed to good conditions for decomposition that is now available for atmospheric conditions. So to finish, just some takeaway messages. So ground ice and carbon estimates face similar challenges regarding the number of data points and the upscaling process, but also face similar solutions. For example, developing better superficial deposit maps for the upscaling process will benefit both the upscaling for carbon and also for ground ice. It is essential to characterize ground ice to better understand and predict carbon release processes because, as I mentioned, soil carbon release through thermokarst is likely to be a larger source of carbon release than active layer deepening of this deep organic carbon, which is not very favorable for deep decomposition of the carbon. And finally, thermokarst processes vary widely depending on local conditions. And by that, I mean that knowing the amount of ice is not enough by itself. It's important to understand and know other factors such as the type of ice, the type of soil we have, and the local climate to accurately predict future changes. That's all I have for you today. Thank you very much for listening.
Thank you so much, Samuel, for sharing your research here. It was really interesting. I learned a lot, and I really appreciate the hard work that you have put into doing this research project.
It's really refreshing to see this body of work, that's for sure. And I'm happy to see that you're thinking about the geological context of permafrost and carbon. Because that's, you know, a lot of the focus on permafrost carbon has to do with peatlands, and we know, right. Many of us know that there's actually quite a bit more carbon out there. So yeah, it's just great to see this. If you go to the model of active layer and transition zone in permafrost, I'm interested in your thoughts on this. Like, I think of permafrost just as defined by temperature, but this is sort of implying that it's defined maybe on ground ice. So,
yeah, that's a very well. I was hoping not to have questions about this. Even the division between, you know, transition zone, transient layer, intermediate layer. Yeah, it's a very good point. I put the picture, of course, because I was saying it, so I wanted some people who are not familiar with it.
Mm-hmm.
Have something to see. Yeah, I think in terms, I'm thinking that having that much ground ice, as I mentioned in the presentation, increases the latent heat of melting required, you know, for a phase change.
Mm-hmm.
So in that regard, so instead of just thinking about just the energy or, you know, temperature of permafrost, it's rather an input of energy and release. I would imagine. I'm just thinking out loud right now. I haven't really thought about this that much.
Oh no, it's just, I mean, it's something that I think we do need to think about, and, you know,
I agree.
Working on terminology,
and I've had this discussion, a couple of times with other researchers. Yeah, I agree. Yeah, absolutely.
Okay. Thank you.
No worries.
I'm done.
We'll talk about it again.
I have a question again, kind of looking for your advice, because clearly you have a lot of expertise collected on these specific types of field data, because of some extensive and really impressive field work that you've done. And I guess it kind of also relates to that kind of definitions question, right? So permafrost, yeah, it's 0 degrees, but you also mentioned that while there is more ice, we can actually protect this permafrost because of this ice. It doesn't degrade nearly as quickly because there's so much latent heat involved there. Now, this is something that as someone who does fieldwork and modeling, I bumped into recently.
Right.
And I'm trying to kind of bring some of these ideas to modeling communities. And I want to understand from your perspective, like, what are the key takeaways that you would advise modelers to think about that, like, maybe if you haven't actually gone to these landscapes, you wouldn't have noticed ever?
Interesting question. So I guess the idea of permafrost as being, you know, a uniform column of frozen ground doesn't really work. And I guess you probably knew that already. And it's quite common to have this ice-rich layer, which we term as the transition zone. And this zone will play, the way I see it, play a significant role in the progression of the active layer, could play a role in protecting it. But in terms of adding more to models, I don't think I can answer this. Yeah, I guess except for, we need to have a good understanding of the amount of ice we have in the ground. As I mentioned at the end, also, maybe the type of ice you have, ice wedges versus segregated ice will make a big difference in how you interpret your landscape. Yeah, that will be my take, my suggestion about that.